All right, let's talk about torque for a few minutes here. Torque is a word that you'll hear pretty frequently when associated with motors. We might refer to a motor as a high torque motor or a low torque motor. And we need to understand what that means. Torque is definitely something different than rotational speed. And in fact, it is really just a measure of how able something is to turn something else, how capable it is of making rotational motion happen. Here we see a kind of classic playground merry-go-round, and you could be a person on the outside pushing the merry-go-round in a circle and applying some kind of a force, and you are at some distance from the rotational axis. And that distance, r, is referred to as the torque arm. And you see there's a right angle there. We're applying a force at a right angle. And even as this person goes around, they'll always be at right angles to they'll be pushing at right angles to the edge of the circle. And so that force will always be perpendicular to the torque arm. So what does this mean? Well, it just means that we've got a way of calculating torque. Torque is this Greek letter tau, and it's a force times a distance from a pivot point. And there's a more complicated version of this, but we're going to keep it simple here and just assume that the force and the torque arm are at right angles. So you can increase torque by either pushing harder or by getting further and further away from the center. And this, of course, is the principle of a lever. If you've ever had a hard time, kind of getting a bolt to move, you might need a longer wrench, and the longer wrench would allow you to move your torque arm out a lot farther. And then for the same force that you can apply, the longer torque arm will create a higher torque. So that's just kind of practical application there. But I want to get us to think about torque in another way as well. So here's our merry-go-round again, and now it's populated with these 8 little kids, maybe micro kids. It's got to be harder to turn the merry-go-round with the kids on it than without the kids. And of course, it would be harder still. Oops, hang on a second. Sorry. It would be harder still if we added 8 more kids onto the merry-go-round. So clearly, the merry-go-round itself represents some kind of rotational inertia, some resistance to rotation, and we often will talk about that as a torque load. How hard is it to rotate that object? What does it take to rotate that object? And so if we remove the kids, then the torque load is low. If we add the kids, then the torque load is higher. And if we add more kids, the torque load is going to be even greater. It's going to take a greater torque to rotate that merry-go-round. So we have both the ability to turn and sort of the resistance of turning, both of which can be referred to as torque. So we'll refer to one as, say, the load torque, and the other will be sort of referred to as the available torque. So let's relate that to motors. Okay, so here's a motor right here, and let's assume that this motor, under the appropriate conditions, has a maximum torque of 100 newtons times meters. That's what you get, of course, when you multiply force times a distance. You get newtons times meters. So this has a maximum torque of 100 Newton meters. We'll return to how you can measure that about a motor and so forth, but let's just assume that we knew that. So now we want this is of course without a load. We want to be able to take something, say a disc like this, and we want to take a disc and kind of connect it to this and have the motor spin the disc. Okay, so this is our merry-go-round, if you will. We can figure out, because there are formulas for this based on shape, size, mass, and so forth, we can figure out what the load torque is. And let's say we knew that the load torque of this disc was 65 Newton meters. Well, this 100 Newton meter motor would be sufficient for the task. You could connect this disc to the motor and it could spin it. Why? It has a maximum torque of 100 Newton meters. The disc itself represents a load torque of only 65 Newton meters. And so the motor will be successful in turning this. It's a little bit like, when you think of load torque, it's a little bit like friction. Can you overcome the resistance to rotating that this disc represents? Now, of course, if the disc was slightly larger, or if we added something onto the disc, maybe we would move the load torque from 65 to 85 Newton meters. That would still work. But once we got to 100 or 110 Newton meters, then the load torque of the disc would, of course, exceed the maximum torque available from the motor, and the motor would stall and it would not be able to spin. And we're going to look at this more carefully, but I think I just want to kind of get that idea of torque and load torque out there for you to think about, and we'll apply those ideas a little more precisely very soon.